According to NASA's Moon to Mars objectives, establishing a continuous human lunar presence will require in situ resource utilization capabilities for manufacturing and construction. To construct safe and durable structures, several types of standards will be necessary to determine material properties irrespective of composition of the material, production processes, source location, and time. A standard is a guideline to perform a type of test, evaluate the results, and define acceptance criteria. They are a necessary tool to perform testing on a uniform and consistent basis. Irrespective of the process used to manufacture a structural material, the material must be tested for strength and performance at scale. Several important gaps exist related to the design and construction of lunar structures. On Earth, structural design is dependent on well-constrained hazards, loads, and serviceability demands. Structural engineers use these and then design using an appropriate factor of safety or targeting an acceptable probability of failure. These aspects are ingrained in codes and standards that have been accumulated from experience over decades and even centuries. The Moon is an extremely hostile environment. Lunar structures will be exposed to hard vacuum, huge thermal cycles, radiation, moonquakes, and micrometeorite impacts. These, combined with the lack of engineering experience in such an extreme environment, mean that engineers must heavily rely on testing of the materials to develop the data needed to design and build safe structures. As an example, let's explore one of the first ISRU structures planned for the Moon, a launch and landing pad. Aside from quantifying the expected hazards, mass, and payload, engineers must know the behavior of the proposed material under the extreme conditions on the Moon to design this. The environmental factors will influence the strength, behavior, and durability of the material. Plus, a wide range of construction materials and technologies are being proposed for lunar construction using in situ materials. Regolith-based materials seem to be quite similar in many ways to concrete on Earth. Regolith materials are expected to be brittle materials. They are also expected to have a low tensile strength compared to their compressive strength. However, there are significant gaps associated with the use of regolith-based materials due to the extreme lunar environment. Several knowledge gaps exist for the design of lunar structures. For example, what is the proper test to obtain the strength of the material? What are the quantifiable hazards the structure will experience during its service life? Many technical gaps also exist. For instance, how would the data from a standard test be used for the design of structures? And overall, what is the acceptable probability of failure for a structure on the Moon? A roadmap to establish the standards is needed because we need to deal with a new construction material that we do not have experience with. To illustrate that, we look at our experience with using concrete, a similar brittle in situ material. On Earth, the design of structural concrete is dependent on testing specified by ASTM standards. The most common standard test for concrete is the compressive test, in which a cylinder or cube test specimen is loaded under axial compression. In structural engineering, the compressive test is important for obtaining structural properties of the material for design. Through ACI code, these values are then used to derive additional structural properties, such as tensile strength, since concrete is difficult to pull by testing in tension. The compressive strength is verified throughout a construction project to ensure a consistent strength is achieved. The end conditions, shape and size of the test specimen, loading rate, and curing conditions all have a significant influence on the values obtained in a given test. Specific procedures have been established to define how these values should be treated when used for design. Some small-scale testing of specimens made with regolith simulants is being done at this time. However, in terms of regolith-based construction materials, The appropriate size and shape of the test specimens will need to be established based on the properties of the material at scale. To address this question and the knowledge gaps mentioned previously, controlled testing should be performed on Earth. A large-scale facility is needed with the capabilities to prepare and test appropriately sized material specimens under the conditions expected on the Moon. Additionally, the solicitations expected must inform the standards needed to safely design structures. This should be a consensus process that involves a broad set of stakeholders. Addressing these gaps is necessary to meet the grand challenge of establishing a continuous human lunar presence and a robust lunar economy. Engineers must leverage the accumulated knowledge about the structural behavior of and design using similar brittle materials on Earth. Testing is needed to determine material variability and to understand the influence of the Moon's extreme environment on proposed construction materials. Only then can we begin to design habitable lunar structures. For additional information, please see the paper mentioned in the description.